Woohoo! Welcome back. Today we're going to be talking about another way of calculating solids of revolution. And this time, instead of using washers and discs, we're going to be using cylindrical shells. It's very exciting. Lowly Worm has cousins who carry shells on their backs, so they're very excited about using shells in math. So we're going to be just having a great old time. So, what does this say? It says sometimes discs and washers will be too hard to work with. And I've got an example here. And I want to take, let me pull it up so you can see it. I want to take this shape and rotate it about the y-axis. So if I'm going about the y-axis, I'm going to get kind of this shape, but then over on the other side. So pardon me, Lowly Worm. So what this will look like is that it'll be a little lump right there, and then it'll rotate around and be another lump right there. Right, and there's going to be a big hole in the middle here, and then the outside will be kind of this wobbly looking cylindrical shape. So kind of cool, like a bowl, you put salad in it or something. And the problem is this is all great. So we're thinking, okay, we get a cross section like this, and that'll go around. It'll create a washer, right, with the hole in the middle. Life is good. And the problem is that the equation for this piece of the graph, the thing that's going to be rotated, is y equals 2x squared minus x cubed. And the thing is if our cross section looks like this is delta y, right? Because it goes up and down. And so we need to find an expression for each of these values in terms of y. So I need to take y equals 2x squared minus x cubed and translate it into x equals blah, 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 blah with y. And that's a problem because solving for x in this expression is, to put it lightly, very, very difficult. So we want to look for a different way to do this. In a perfect world, I go on to say here, it would be awesome to set it up with rectangles parallel to the y-axis. So what does that look like? Well, here's the y-axis. Here's the x-axis. Here's by not great picture, but pretty good. And here's a picture of the cross section. Now, if I did a cross section like that, here, see the width there, that's delta x. And so the expression for this point and this point could be in terms of x, not in terms of y. And we've already got it in terms of x. So this point would just be whatever y is, 2x squared minus x cubed. And this is delta x. Everything is great. We don't have to translate into y. And so this is awesome. And we think, yay, let's do that. But the problem is if we're rotating around the y-axis and we take a cross section that's parallel to the y-axis, it's not going to make a washer. It's going to go around, and it's actually going to make a cylinder. Dun, dun, dun. The plot thickens. Ta-da! Through the magic of television, I've already prepared this. Minions are hard at work making these images for you so that you can, to help you visualize what's happening. So this is the picture from the book. You might have guessed that. This shape is called a cylindrical shell. It's called a cylindrical shell because we're not going to consider the entire cylinder all the way through. We're just going to look at a very tiny depth, which is going to be delta R. Now, hopefully, pardon me, let me move. I know, Lowly Worm is very excited because, again, shells, right? Worms not dissimilar to snails. So some of his favorite people are snails, and they have shells. So, this is all mathy and exciting. If our cross section goes like this, then our delta R in this case is actually going to be a delta X. So it's going to follow exactly the same rules that the washers and the discs followed, is that if you can find where that little tiny delta width is, you can figure out whether you're going to be working with X or with Y, right? So we're going to be making shells. Now, since it's shells and not discs or washers, we've got a new formula. Let's take a look here. This formula says the volume of this shell is 2 pi r. Now, 2 pi r, that's the circumference of a circle. So this is how far around the circle is. H is the height. So we're going to take a bunch of these rings and stack them. So it is, in a way, we're still working with washers. It's just that rather than looking at the difference between the inner and the outer radius, we're actually going to use H to take that place. So instead of it being a really flat washer, this is going to be a cylinder. So we've got a slightly different formula. So there's the circumference, there's the height, and there's the width of the shell. So now you have a second formula to think about. If you're using washers and discs, you're going to be looking at the difference in the areas of circles. And here we're going to be, rather than the area of the circle, we're looking at the circumference of a circle and stacking it up high. So we include the height. So it's a little bit different, but this will allow us to solve this problem. So this first example, use cylindrical shells to solve the problem we started on the previous page. So this is a lovely photo of what's going on. I guess it's not photo, it's drawing. Pardon me. And here's the height right there. Notice that at any point, here's another cross section right there. At any point, the height is just whatever y is, which is the 2x squared minus x cubed, right? The height is because we're going all the way from the x-axis up. And that's another reason that it's nice to use cylindrical shells. If you have something sitting on the x-axis like this, you don't have to be subtracting anything. It's really nice. It's just the height, and it's just easy peasy that way. So let's look at, you guys ready to look at the nitty gritty? Hopefully you've been working. I made that suggestion. Really make sure you set the first two sections before you come into this section, because this is going to be a little bit different and you don't want your brain to be trying to hold all of them at once. So definitely do the first two first, and then let's do this one. Let's take a look at it. Okay. The volume. We're going to sum from 0 to 2. So let's stop there for a second and say, why the heck is it 0 to 2? Always check the details. Why does it start at 0? It starts at 0 because that's the center, right? We're rotating this around, but we're only going to count over here on the right. Why don't we have to count over on the left? Well, because we're rotating it around. So the cylinders take care of that. We only worry about this piece, and then the cylinder takes care of the whole rotation. Okay, so we're going to go from 0, and then how do we know this is 2? And the answer is we were actually told this in the beginning, but you can also graph it. So if you look here, we could argue whether it's obvious or not. But if you try to solve this, if you said, when is 2x squared minus x cubed equal to 0, right? Then what would you get? You would factor out x squared, and you get 2x. Oops, sorry. No, you wouldn't. What? What would you get? No, you would not. You would get 2, if I factor out an x squared, minus x. And then by the 0 property, either x squared equals 0 or 2 minus x equals 0. Can you guys see that? Not quite. There we go. So x equals 0 or x equals 2. And so that's how we get these 2 points. So that's how we get the limits, the bottom and the upper, lower and upper limits for the integral. Now, what is 2 pi? 2 pi comes from the original formula. Remember, 2 pi times the radius. Now, what is the radius? The radius is how far from the center the cross-section is. Now, since the center is right there at the y-axis, the cross-section is just wherever x is. So this makes it really easy. So the radius is from the center out there. That radius is going to just be the x value. Okay. What is the height? The height is this piece, and that's just whatever y is. Now, as soon as we go to the next step, that's going to be 2x squared minus x cubed. Okay. And then what's the width? Now, the width is the little tiny guy right there. And that, in this case, is a dx, because originally, what was it? It was a delta x. You got it. Now, when would it be a delta y? It would be delta y if this were the other way around. If it were long ways, right? If we're lying kind of along the x-axis, then our width would be delta y. But it's delta x because that's where the skinny part is. What do you guys think? What do you think about that? It's not too bad, right? Pretty okay? Woohoo! Now what? Well, now, even though my paper is fighting with my lamp, we're going to go ahead and look at this and go, okay, yeah, you could probably do something creative with, solving this integral. But again, I'm always just going to take the simple way out. I'm going to say the 2 pi, those are constants. They don't need to be part of this. They can wait. And then I can say this x can go multiplying through. So then I get 2x cubed minus x to the 4th dx, right? So the x multiplies through. And then I get 2 pi times, and here I have to use the power rule. Again, very nice and simple for these. This is going to be 2x to the 4th over 4 minus x to the 5th over 5. And I'm going to evaluate that between 0 and 2. And I've got another piece of paper all ready for us. So the volume is going to be 2 pi times the quantity 2x to the 4th over 4 minus x to the 5th over 5 between 0 and 2. Woohoo! And so now what? What do we do with that? So now all I do is I evaluate this at 2 and at 0. So this is going to be 2 pi times. Now, you could go ahead and cancel this. I'm just going to worry about it when I sort it all out later. So this is going to be 2 times 2 to the 4 all over 4 minus 2 to the 5th over 5. And I'm going to subtract 2 times 0 to the 4th over 4 minus 0 to the 5th over 5. Now, a lot of you are asking yourselves, oh my gosh, why do you always bother with this? Because when we plug in 0, we always get 0. The answer is you don't always get 0. And yes, I know this is going to be 0, but I don't know if you know it's always going to be 0 in cases like this. And in fact, if our integration involves something more exciting, something like a square root of x plus 4, or even trigonometry, this would not necessarily be 0. So it's a good idea to always plug in the 0. Just double check. I'm just saying, you don't have to. I can't force you, but I can encourage it. Okay, 2 to the 4th. 2 times 2 is 4. 2 times 2 is 4. 4 times 4 is 16. 2 to the 4th is 16 times 2 is 32 over 4 minus 2 to the 5th is just 16 with another 2. So that's 32 over 5. It would be so cool. And of course, this is 0. It would be so cool if we could actually connect the dots here. We really, really can't. So now it's up to you. And what I'm probably going to do to simplify this, there are a couple different ways. You may actually find it easier to convert these both to whole numbers or mixed numbers, because that math isn't too hard. The other thing to do it is to notice that this does reduce. So you get 2 pi times 8 minus 32 fifths. And then you can convert this to a decimal. I mean, that would be the engineering way out. Or we can write this in terms of fifths. So 8 in terms of fifths, how many fifths would that be? You got it. It's 40. Woohoo. Okay. So then, in my attempt to draw this out as the longest math problem ever done, I get 8 fifths inside times 2 pi, and that's going to give me 16 pi over 5, I think. That's my volume. Woohoo! Yay! Okay, so far so good. Now, if someone were to come up and ask you, where did the pi come from? Where are you getting pi? The answer is generally going to be the pi is coming from the fact that you're rotating these objects around an axis. So you're involving circles, either tall circles, which are cylinders, or short circles, which are discs, or short circles with holes in them, which are washers, right? So we've got short circles, these are discs. Short circles with holes in them, washers. And then if you go for this one where it's tall circles, which is technically a cylinder. Now for discs, if the disc is oriented this way, this is a delta Y. The washer, this is a delta Y because this is the skinny side. Here, this is going to be a delta X. And then if you took your paper and it reversed, they were going the other way. I can't get them all in the video. Sorry about that. It would reverse it. This would be delta X, this would be delta X, and this would be delta Y, right? Just depends on whether or not it is up and down, delta Y, side to side, delta X. Woohoo. Okay. You guys ready? Take a deep breath. We're only at 18 minutes, so I think I'm just going to push on through. Let's go ahead and there's one more example I want to show you. And it looks pretty cool. And Lowly Worm might be interested because this always looks like it's kind of like an insect to me. Don't those look like wings? And we're going to spin it around, which again is going to look kind of interesting. The outside of the object, the outside of the region, is rounded. So when you spin it around, see I'm spinning it around the y-axis, you're going to have a rounded bowl shape on the outside, kind of round, like that. But notice that the inside, the sides are straight, so you're going to have a conical hole. So that's kind of cool. And so, one way to approach this would be, if you can figure out what the whole object is, you could just find the volume of the whole thing and subtract out the cone. That would be kind of cool. Unfortunately, I've asked you to do something twice. So I said, find the volume of this, but those of you who've been looking at the screen, you might have noticed, oh no, we have to do it both ways. Yes, because this problem can be done both ways. So let's practice. Let's look at how it looks differently. So, you guys ready? Lowly Worm, I'm going to ask you to step aside because I'm going to have to use the paper. He'll be back. He'll be back. He's still very proud of you. You are very brave doing this. Okay, so shells means cylindrical shells, as opposed to like shells and cheese, although those are also delicious. Okay, so if we're asking for shells, then that means that our rotation and our these cross section are parallel. So our axis of rotation or our axis of revolution and our this little cross section are going to be parallel. Does that make sense? And I'm going to give you a preview of the next page. Oh no, I didn't write it out. I didn't draw it out yet. Okay, never mind. I thought it was pre-drawn. It's not pre-drawn. I was just going to compare and contrast, but we're going to have to wait till we get there. Okay, so I've got the cylinder. The shell height is... Okay, so let's look at what's happening. This guy right there, is that a delta X or a delta Y? You got it. It's a delta X. So we want everything to be in X's. So I need to know this point minus this point, right? So I'm going to do A minus B. Right? That's the height of this particular cylinder. Okay, what's point A? Point A is y equals x. So this one is going to be, which one is it going to be? This one's going to be x. And B, the round, is going to be x squared. Now this is surprising, right? Because a lot of times you think of x squared as being bigger than x. So x minus x squared, like my initial thought is, oh no, is it going to be negative? And the answer is, what are the values? We know that there's a 0 here. When does x and x squared intersect? Right there. When does x equal x squared? Well, when it's 0, right? 0 equals 0 squared. Where else? You got it. It's at 1. So this is where x equals 1, because then x is 1 and 1 squared also 1. So this is the point where x equals 1 and y equals 1. Okay, between 0 and 1, which means we're talking about fractions, a fraction squared is generally smaller than the fraction itself. Depends on the fraction, but fractions less than 1, absolutely. Okay. Do not panic. Do you recognize there's the circumference, there's the height, and there's that delta x, which becomes a dx? And I said, do we use this one or do we use this one? And the answer is, since we've got a delta x, since our cross sections are going here and our rotation is going here, we use this one. This would be if our cross sections looked like this. So we had delta y and we were rotating this way. That would be this one. Does that make sense? So this one rotating around this way is dx. This one rotating around this way is going to be dy. So we're going to use this. And my r, what is my r? My r is the radius, the distance from the center, or the rotation. So how far is this cross section from the center of the rotation? And the answer is, oh, it's just at x. That's just x. Isn't that convenient? Now, when would it not be x? Well, remember a couple of videos ago, we had, instead of rotating or revolving around the y-axis, we went to like x equals -1. and then everything was bigger than x, it was x plus 1 or x plus 3 or something bigger, that's when this would be different. As long as we're just moving out from the axis, generally the radius is just going to be x, or in this case it would be y. Okay, what's the height? Well, we got the height already. I prepared you over here. You have to remember, figure out who's on top, who's on the bottom to figure out the subtraction. So x is on top, x squared is below during this little region. So we get x minus x squared. So far, so good. Width of each shell is delta x, because again, it goes side to side rather than up and down. Oh, you can't see that. It goes side to side rather than up and down. Okay, so this is delta x. That's this one. This one is the one we're doing here. Woohoo! Okay, so through the magic of television, I've already put it all together. So there's the 2 pi. The r is x. The h is x minus x squared. And the width, delta x, becomes dx. And again, this looks terrifying, but remember, 2 pi hangs out outside. I've got from 0 to 1, and then I'm going to multiply through because that's going to make this way easier. So it's x squared minus x cubed dx. I use power rules. Woohoo! So it becomes x cubed over 3 minus x to the 4th over 4 between 0 and 1. I check in with myself. I say, yay! Isn't 1 lovely? Don't we love 1? 1 is so much easier than 2 or 12 or 143. And then we think about it. We go, well, when I plug in 0, I'm just going to get 0. So all I need to worry about is 2 pi times 1/3 minus 1/4. Because I plug in the 1s. And now I'm going to show you one more thing. So this is 2 pi times 1/3 minus 1/4. And there's a very cool thing that happens when you've got fractions like 1 over 3 and 1 over 4. So, least common denominator, 12, you got it. 1/3 converted to 12 is 4/12. 1/4 converted to 12ths, 3. You got it. So if I take 1/3 minus 1/4, that's really just 4/12 minus 3/12, and that's 1/12. And hopefully you are asking yourself, does this work if instead of 3 and 4, I use 2 and 3, or I had 4 and 5? And the answer is yes. If you've got 1 over a smaller number minus 1 over a number that's 1 bigger. So if this is 3, 4, 4, 5, 6, 7, 12, 13, as long as they're different by 1 and you're subtracting them, you end up with 1 over whatever the LCD is. I don't know if it's worth memorizing it, but it's just a cool trick that always works. Okay, so that's 2 pi times 1/12. Can you guys see that? Yes. That's 2 pi over 12 or pi over 6. Oh my goodness. I'm so excited. Now, we got one more problem to do because I told you we were going to do this a second time using washers. You guys ready? Remember, you can pause videos. I can't pause recording, but you guys can pause it. And then, so if we're at 30 minutes, it's probably going to be a few more minutes still. So don't feel bad at all. Go ahead, take a break, pause the video. I will be here waiting for you when you get back. I am happy to wait for you. In fact, let me just stop right now. We're going to stop everything. Okay, go ahead and pause me. I'll be here when you're back. Go get a drink of water, blink your eyes a couple times, walk around so your legs aren't all stiff. Okay? Okay, I'm waiting. Go ahead. Okay, ready? Woo! Let's do it. Okay, we're going to work on washers. So the first thing we need to do is we need to remember what the heck this thing looked like. So let me remind you, we got Y, we've got X, and we've got, interestingly enough, we've got Y equals X. Can you guys see it? Yep. And then we've got basically a parabola, right? Y equals X squared. We know this point is at 1, 1. We know this point is at the origin, and we know we're going to rotate it around the y-axis. So what are we going to do for our cross-section? And so you got to think about it. If you take up and down and you rotate it around, you're going to get a cylinder. How do you get a washer? Something like this, going around, makes something nice and flat that goes around. So we're going to be looking at cross sections that look like this. Okay, let's review. If your cross section looks like that, what delta is this? You got it. That's delta y. We have to put everything in y. Do not panic. We can do that. This is not so hard. The previous problems, they were a little tricky, but this one, not so bad. So we need to be able to find these 2 points so we can get the height, right? Or in this case, it's the difference in the radii. Sorry about that. It's not the height. It's kind of the height. Shh, don't tell anyone. But it's also the difference between the outside radius and the inside radius, right? And that's how I've written it down below. So we want to know what the big R minus the little r is. So who's the outer radius and who's the inner? When you look at this, you think about, okay, so I'm going around, who's on the outside? I claim the outside, the bigger radius is going to be the y equals x squared, and the little radius is going to be the y equals x. Do you guys agree? Okay. Now we've got our delta y. So when we go down here and I give you 2 formulas, I say the volume is either pi, this is remembering back to the last one, the square of the outer radius minus the square of the inner radius, or the square of the outer radius minus the square of the inner radius. The difference between here, we're going to use dx, here we're going to use dy. Which one are we going to use? So if we look up here, we've got this cross section. It's perpendicular to the axis of revolution. And so here we've got washers. This is delta y. We're going to use this one. Okay. So for this case, the outer radius is y equals x squared. Oh, I'm going to skip that for now. The inner radius is y equals x. So what are we going to use? Remember, it all has to be in terms of y, and it's the y equals x line. We want to know what this inner radius is. So this is x, which is equal to y. So this is going to be, we're just going to use y as that radius. Now, why is this a problem? Well, for this, for the outer, this is the inner. There we go. For the outer radius, this is y equals x squared. I want to know what x is in terms of y. So if I have y equals x squared, what is x in terms of y? Y equals x squared. How do we get to x by itself? Take the square root. Now you should ask me, wait a minute, are we allowed to take the square root? What if y is negative? Let's check. Is y ever negative here? Thank goodness. So we don't have to worry about this. So we actually have x equals radical y. So here we're going to use square root or radical y for our outer radius. So we got our outer radius and our inner radius. And what was the width of the washer? Was delta y. Okay, you guys ready? This is very exciting. Notice through the magic of television, I kind of had it all written down already. We've got our outer radius. It's going to be squared. Isn't that brilliant? So when I look at this, I was all worried. But in fact, when I square the square root of y, I get y. Minus y squared all times dy. Okay, pi comes out. Pop the pi out. And I've got y minus y squared dy. I'm going to use the power rules over here. So I get pi times the quantity y squared over 2 minus y cubed over 3. Okay, between 0 and 1. This is pi times, now when we put 0 through, we're just going to get a bunch of zeros. So I'm not going to worry about it. I'm just going to plug in the ones. 1 squared, 1/2, 1 cubed, 1/3. Remember that rule I gave you before? 2, 3. What does the difference equal? The difference is going to be 1 over 2 times 3, which is pi. Do I have space? Oh my goodness, it's so little. Times 1 over 6. So that's pi over 6. Wait a minute. What did we get in the last one? When we did it using shells instead of washers? Oh my goodness. Celebration. Woohoo! The town is saved. Look at us. We got the same answer for both, which is really awesome. Now, if you're looking at me like, what just happened? That's fine. That's absolutely fine. You should always ask these questions. So how do you do this if you're not going to be silly like me and using these old-fashioned rules that I sometimes remember and sometimes I forget? Well, if you don't use old rules like that, that's fine. All you do is come up with the least common denominator. In this case, it's going to be 6. 1/2 gives me 3/6. 1/3 gives me 2/6. What do you guys think? Okay. And so 1/2 minus 1/3 is 3/6 minus 2/6. That's 1/6. Oh my goodness. So we get, if I don't draw too far for you guys to see it, 1/2 minus 1/3 is 1/6. That's pi times 1 over 6 or pi over 6. Same answer. Yay! You guys are awesome and amazing. And this was nearly 40 minutes of hardcore math. So yeah, I'm sure in decades to come, we will question whether I should have gone ahead and done this as one video or maybe split it into 2. But we are at the end. You guys are amazing. We've got, in these few sections, we've got a couple different formulas. And one of the reasons why I wanted to do this problem 2 ways is, even though it's a little smeary, and I'm sorry about that, I was able to collect the formulas, and both for, right, cylindrical shells and for washers, which are kind of like discs. It's that they're considered together. So if you go in here, I'm trying to find where I put the formulas. Right, I gave you the formulas for cylindrical shells there, and I gave you the formulas for washers here. And in fact, I mean, the formula for discs is just a single radius. A single radius. So there's discs, there's washers, and here are the shells. So you've got all these formulas together. It's a lot. And again, I'm going to recommend that when you study this, and Lowly Worm is also going to recommend that when you study this, Study them separately. Do all the homework for the washers together. Do all the homework for the discs together. Do all the homework for the cylinders together. And then once you feel comfortable about each of the different types, then start comparing and contrasting. See if you know how to do it. Just in case I do something nasty, like I give you a test where I specify that you have to use a particular method. Because sometimes, like this one, the problem we just did, you could use either washers or shells. Okay, you guys are awesome. I've talked for 40 minutes and 9 seconds so far, so let me let you go. Remember, get something to drink, give yourself a rest, give yourself a gold star for the day. You're amazing and incredible. And I hope you have a really wonderful day and get lots of whatever it is you need in your day. Try to get lots of it. Whatever that bliss is, get lots and lots of bliss. And then come back and do some more math homework. Because, math homework, it just makes the day better, right? So, and I will see you in the very next video, which, spoilers, is going to be a lot of work. Okay, that was a little physics joke. Very, very small physics joke. Lilyworm is not sure he's going to be part of this. So, and the sound of my cats fighting under the table where I'm recording this tells me I should go. So, I will see you guys in the next video. You guys are amazing and wonderful. Woohoo and math on.